I'll be your presenter. This module addresses DNS best practices and troubleshooting. An auto run of this presentation takes about 20 minutes. Let's quickly review the table of contents page before we begin. This slide is your table of contents. During the presentation, you can click on the TOC link to return here at any time. Each bullet item above is a link to the topic allowing you to navigate the presentation as you see fit. Clicking back will return you to where you left off. If you allow the presentation to auto-run, you will see each of the topics in the order shown. This presentation discusses the issues around DNS best practices and how to optimize your DNS environment. The second group of topics deal with DNS troubleshooting, including inconsistent name server behavior and delegation issues. Some of the most commonly used best practices. We'll discuss each of them in the following slides with illustrations indicating how they might impact your topology. Let's dive right in. A forwarder, just another way of configuring a named server, is used to reduce the amount of network traffic from internal clients to the outside internet. This is useful when the administrator wants to protect his internal named servers from the internet, yet wants to provide query access for internal clients. Once the named server is designated to be a forwarder by the master named server, all the offsite traffic will be routed to the forwarder, greatly protecting the internal named servers from attack. The forwarder does name resolution for internal clients for its zone, a.com in this example. All queries intended for the internet will be served from its cache if possible. Configuring a named server to be a forwarder could not be simpler. You do nothing on the forwarder itself. All configuration happens on the authoritative named server for the main zone. Organizations normally have their full primary namespace available from inside the firewall so that all corporate clients have access to all corporate resources. This is not normally the view that an organization wants to present to the outside world. Thus, a second name server is set up outside the firewall to provide those services under the same name that are appropriate for external consumption. This external server will have access only to necessary hosts responsible for services to the external world. Recursion should be disabled and transfers restricted to known servers only. The split of the namespace can be accomplished with bind views. For better performance to outside consumers while isolating your internal users from internet loads, you should have multiple external servers geographically separate from one another. This means that administrators are implementing a strategy where he is maintaining zone data in geographically dispersed areas to increase availability and improve performance to the end user. This offsite strategy might be a regional office away from the headquarters and the primary data center. These servers should be delegated and/or be slave servers, and as seen in the previous slide, should be restricted to transfers from known servers only. The topology diagram gets a bit complex when we add in hidden masters, so let's review. Just to the left of the forwarder is a designated slave of the internal prime master. In the upper left, we have our external namespace, on-site and off-site slaves. We have then hidden primary masters, one for the internal namespace, one for the external. Hidden primary masters are not visible or query enabled by external clients and give us better disaster survivability. You hide a server by not creating the normal NS records that would have described the server's to other servers in SOA queries. Both external and internal hidden masters should have recursion disabled and restricted transfers. Since they are masters, they need protections by firewalls, and this can also be done with bind views. The next best practice step is easy to understand. Each major component is critical to your business. Protect your major components with high availability wherever it makes sense and wherever you can afford to. Certainly you want to consider the use of high availability for your primary masters and your most critical slaves, both on-site and off. Most HA technologies rely on failover technologies. So in your disaster recovery plan, don't forget to plan and include periodic actual failover testing. For this diagram, let's focus in on the internal namespace only. The internal namespace itself can become complicated with many scattered devices that move and change often. Breaking up this namespace into separate independent zones can greatly simplify administration and improve overall performance. When doing so, though, make sure that you give attention to building in reliability to each of those delegated zones. DNS and bind can improve branch office performance. A resolving slave server can be put at the remote office to cache and thus reduce WAN traffic. You can also preload slaves with corporate zone data so that they can resolve queries locally. These local slave servers may be configured to be hidden. With this slide, we want to bring all 7 practices together. We started with the use of forward resolving servers. Then we distinguished between the internal and the external view of the main corporate zone. We talked about having multiple geographically separate external name servers. One might be on-site at the data center and one off-site. Then we introduced the notion of hidden masters. Regarding the internal namespace, we talked about 2 best practices. First, the replication of DNS infrastructure at major company divisions, and then, second, regarding branch offices that must still be on the internal side of the namespace, we talked about the use of resolving or hidden resolving slave servers to build rich caches from which the local queries can be answered without going to the data center. To really improve the uptime of a network as a whole, we talked about identifying servers which are mission critical and deploying high availability technologies. Throughout most of these slides, we noted that you should configure these servers not to allow unrestricted transfers or recursive queries. Now we're going to change directions a bit and start walking through a series of common troubleshooting scenarios. Our first one is a very common problem. What has just happened when you noticed or discovered inconsistent zone data being returned by different clients? Both servers are properly authoritative for the zone in question, so how could they return different results? In this case, you should first compare the SOA records of the 2 servers to see if there's any conflicting data or serial numbers. In our example above, the 2 serial numbers are identical while the addresses at the bottom are clearly different. This looks like a change was made to the primary without incrementing the serial number, which does not trigger an update when the independent slave checks the version of data it holds. The primary server, ns.opus1.com on the left, most likely needs to increment its serial number so the slave will know its data is obsolete and will refresh itself. This is the next challenge, and most DNS admins run into this common situation. You just changed an A record, but the system refuses to answer queries with the new data. What went wrong? Compare the zone data file on the disk and the query done through NSLOOKUP or DIG. In this case, note the serial number and hold on to it for a moment. The bottom line shows the new address we expected to see propagated. Then, using NSLOOKUP or DIG, examine the DNS environment on the primary server for the zone. In this case, compare the first address to validate that the primary really still has the wrong address. Then compare the serial numbers, and sure enough, the edit copy on the disk has been incremented as compared to what is on the primary. This is what things look like when a change is made, but the zone has not been reloaded. In this situation, we're examining the zone data for a given zone on different authoritative slaves. Both should be identical, but clearly they are not. These serial numbers are different along with whatever else caused you to begin debugging in the first place. After checking the config, always start troubleshooting, working your way up the OSI model. A simple loss of connectivity can cause this. A new or modified firewall can do this. A typo can do this, resulting in a hard disconnect. Bind can be very picky about syntax errors, and an error in the zone data file can cause this result. This example shows bind erroring out on a zone record syntax because it doesn't recognize wins. This is another scenario that happens a lot. You add a DNS record, but a query returns with the NX domain error message. The cause for this situation can be found in the zone data file. At the top line, we track the results of the Unix cat command for the zone data file db.dns.pn. On the third line of the result, we see the origin declaration specifying dns.pn for the SOA record. Then down on the last line, where the CNAME record is set up, note how the field is entered, www.dns.pn with no trailing dot. Later, when the CNAME record is referenced, the origin string will be concatenated, creating a non-existent domain name. Don't forget that dot at the end of your domain name declarations. For our next situation, imagine that you set up a new subdomain and everything seems fine, but queries to it error out. We, as an external client, send our iterative queries to the delegated server for dhcp.hm. It in turn sends or tries to send our query over to a delegated server for uk.dhcp.hm. This should work because we tested the servers responsible for uk.dhcp.hm and all seems well. Since we don't get a response back from uk.dhcp.hm, we send the NX domain error back to the original client. From the server we think of as Delegator, we see no recognition of the uk.dhcp.hm zone. In this example, we use NSLOOKUP, change the server in question, set the record type to NS, and set debug mode. Finally, the last thing we do is query the zone and get the report that follows. Note the R code is NX domain. The auth indicates that this is the answer to the query. Down at the bottom of the question section, we see that the zone couldn't be found for the server. Thus, the delegation is not properly set up for this server. An authoritative response is important, and a delegated server that doesn't answer authoritatively is a problem. In this example, a client queries for dhcp.hm from the master for the HM domain. This server refers to the query to ns3.opus1.com, who is supposed to be an authority for dhcp.hm. In this case, it is not. What would cause this? To pursue this problem, we look first at the system responsible for delegation, ns3.registry.hm. In the results, we see that ns3.opus1.com is properly listed as the authoritative server for our zone, dhcp.hm. All looks good here. We need now to check the delegate itself. On the delegated server, we do see a problem. With the debug mode turned on, we see no error code is returned. But we also don't see the authority bit flag. Lacking this flag, the server cannot think of itself as authoritative for the zone, even though its name shows up in the answers portion of the query results. This is another example of lame delegation. This completes this DNS DHCP Fundamentals webinar. We thank you for taking the time and invite you to review all the webinars in this series.